Okay, so so this took a little long, but so last time we talked about in our reinforcement learning lecture, we talked about Markov decision processes and how we can actually solve these processes using Bellman equations. So I wanted to put out all the different forms of the Bellman equations up. So we have some idea of where the different algorithms we're going to see today come from. So these are all the same. Well, there are two equations actually. 1, 2, 3, 4 is the same equation, and 4, 5, 6, 5, 6, 7, 8 is the same equation. But they come in different forms to make some math and some algorithms easier. So in particular, we have two types of value functions defined. V is the state value function that basically tells you what the long-term expected return from that state is. And Q is the action value function. It takes a state and action and tells you what the long-term return from that state taking that action is. Remember that the general setting of the reinforcement learning problem is sort of like a game that we play with the environment. So in this game, we start at a state S, and then from here we decide on what action to take. So these are the different actions, and then it's the environment's turn. The environment decides what rewards to give us and what other state to send us to. So after this, we're going to have something like some reward and some other state. Okay. So, and then from this other state, we're going to decide on some other action again. Prime, and this thing is going to keep going. So in this sort of like a little game tree, let's say the white nodes are the things that we decide, and the black nodes are the things that the environment decides. So we decide what action to take, the environment decides the reward probabilistically and the next state probabilistically, and then after that we decide what action to take again, and then it basically goes back and forth. Okay, so given this type of situation, how can we actually compute a value function? We can compute a value function sort of recursively. So equation 1 basically says, well, the long-term value from S is basically depends on my policy. That's why we subscript with pi. Pi represents policy. Pi A given S is the probability that we're going to take action A in state S. And so we take an expectation over all possible actions we can take, the probability of that action, and then the Q value of what that state action pair will give us. And the Q value in return says the long-term value you will get from this state action pair is the immediate reward you're going to get, which is equation 2 RAS, plus the discounted sum of gamma is the discount factor. Sum over all possible states we're going to end up in, all possible S primes, the probability of getting into that S prime, and what the long-term value of that S prime is. So the first two equations define V and Q recursively, mutually recursively in terms of each other. But we don't have to do it that way, and a lot of algorithms just work with V or Q. So equation 3 is basically the equation 1, where instead of Q, I basically substituted what Q is equal to, so that I can write V in terms of V. Okay? So if you look at equation 3 carefully, it says you're at state S, you're going to take some action with probability pi A given S, and once you take that action, then the reward you're going to get is the immediate reward R, SA, and then the discounted version of whatever S prime you're going to end up in, that's the environment's decision, and then what the value from that S prime is. Okay? And the last one does the same thing for Q. So these are sort of the expected Bellman expectation equations. All of them can be summarized by saying your long-term reward is the immediate reward you're going to get, plus the expected reward that the next state is going to give you. Any questions? So this answers the question, what is the value function for a particular policy? The other question we want to answer is what is the best policy, or what is the value function under the optimal policy. So that's where the Bellman optimality equation comes from. Again, 5 and 6 are the mutually recursive definitions. So V star is the optimal value function, and V star of a state is basically the maximum over all possible actions of Q star SA. Okay, so let's say we already know the Q's. So you're looking at your different actions. Each action basically has the value, long-term value Q star SA. And we're talking about the optimal policy here. So the optimal policy is obviously to take the action that will lead to the highest reward. And Q star SA is again defined recursively as the immediate reward, RSA, plus the discounted version of sum over all the possible states I might end up in, the probability of ending up in that state, and the V star of that state. Okay? So why is that a sum and not a max in equation 6? Since I'm trying to maximize everything, why am I not taking a max?
We know the action.
Right, we know the action. But why is there a sum over S prime rather than a max over S prime?
The environment decides where you will end up.
That's right. So we can't maximize the environment's responses to us, right? So we don't know what the environment is going to do. The environment is flipping a coin and throwing us to a random S prime, and we have no control over that. So we keep that as a sum. That's an expectation to represent the expectation over environment's uncertainty. Okay? But we can do a max in our actions because we get to choose the actions. Similarly to the previous set of equations, 7 and 8 are basically combining 5 and 6 together to express V in terms of V and Q in terms of Q. And it's just plugged in. And notice that in both 7 and 8 we have max over actions where we actually have control, and sum over states where we don't have control because the environment is going to decide the control. So in these things we have control, so we can take a max. So over here we can take a max, but over here we can't take a max because the environment is deciding where to send us. So everything else we're going to see for the next few lectures is basically applications of these things. So are there any questions about these equations? Okay. So let's directly come to our first algorithm. So first of all, we have just like we have two different Bellman equations, we have two different problems. So what's the first Bellman equation tell us? What is the value of a particular policy, right? Sorry. So that's the problem of prediction or estimation of value. What's the second Bellman equation tell us what's the value for the optimal policy. So we call that the problem of control. Okay, we'll see algorithms that solve both of these problems. Given a policy, estimate the values, and then given an MDP, find me the perfect policy. So the first algorithm here, iterative policy evaluation, solves the first problem. So somebody gives you a policy and says, okay, what is the value of each state in this policy, or each state action pair in this policy? The solution is really simple. We basically start with all the states having 0 value, and then we use the Bellman equation to update them as many times as possible until it converges. Okay, so basically iterative policy evaluation, this algorithm corresponds to equation 1, or rather equation 3 here, being continuously applied to update the V's. Okay, so imagine you have a game with 100 states. So V is a 100-dimensional vector. You fill this vector with zeros in the beginning, and then you use equation 3 to update the next V by looking at the previous V's. Okay? And you keep doing that. Is that clear? Okay, we'll see that this actually converges, and it converges to the right values eventually. So here's again the equation that we're using. So here Vk and Vk plus 1 correspond to different iterations of the algorithm. So Vk was the last iteration, and I basically have a bunch of values for each state in Vk. Vk plus 1 is going to be my next better estimate, and Vk plus 1 is computed in terms of Vk using the Bellman equation directly. Okay, so assuming we understand all this, here's a little exercise for you. So get some paper and pencil out and find the, do 3 iterations of this on this little puzzle. Okay. So everybody has 5 minutes to do that, and without paper and pencil, it's going to be really hard. So please find paper and pencil. So the game here is we have a 4x4 grid world. The actions are north, south, east, west. The upper left and the lower right corners are shaded squares. They're terminal states. You don't get out once you get into them. If you're on the left side and you take a left action, it has no effect. You stay where you were. Reward is -1 for every step until you reach a terminal state. And the agent, the policy that you're evaluating, is the uniform random policy. So you have 1/4 probability of going left, right, up, down. Is the game clear? So V is a function, V is a table of 14 values. So in the beginning, you're going to basically assign 0 as a value to every each one of these 14 states. So that's your first iteration, or 0th iteration. And then you're going to apply the Bellman equation to get the next set of V values, V1.
Value of the terminal state and the rewards of the terminal
0. You stop suffering and get taking -1s for each action when you die. I can keep showing this, or I can keep showing the previous slide with the equation. Actually, I can probably do both by making this smaller. see the equation as well. So if you can go at least 2 iterations, that means you understood what's going on. If not, ask me a question.
Transition properties are 1, right?
0.25. So you have equal chance of going left, right, up, down.
That's policy.
Oh, sorry, yeah, transition probabilities are basically there is no uncertainty wherever you want to go, you actually end up there. So what does V1 look like? I told you what V0 looks like. V0 looks like a bunch of zeros on every state, on every cell. What's V1?
Value of the first.
After the first iteration, after you do the update based on equation number 3 once, starting with a 0.
3
There you
over,
Hmm?
3 over 4, 0,
Minus.
minus, sorry.
Minus 3 over 4. Why?
So,
Well, I mean, I'm looking at 3. You have 4 actions. You're taking a sum over 4 actions. Pi for each action is 1 over 4. And then inside you have the reward, immediate reward for that action, which is always minus 1.
you ask for state 3 or 1?
V1. V1 meaning when you do this application for 1, I'm asking about all the states at iteration number 1.
So you're saying for state 1.
Yeah, I answered for state 1 after the first iteration.
After the first iteration, state 1 should be minus 1.
But isn't the terminal state's reward 0? You said that?
No, every action gets minus 1. After you get to the terminal state, then it's 0 forever.
Okay,
But
so
stepping into the terminal state still gives you a minus 1. So, in other words, after 1 iteration, we have minus 1s everywhere.
Let's say we are in state 1 and we want to go up.
Then
To
it
get
says
minus
actions leading out of the grid world leave the state unchanged. So you
Okay.
end up in the same state,
1, but I get the reward.
you do get minus 1, yes.
4 times.
Yeah. Which cancels out, and you basically get minus 1s everywhere. And then when you do this again, what do you get? After the minus 1s, what's the next iteration you do? Now it should make a difference whether you're next to a state, terminal state or not. So let me show you. So these are the first 2 iterations, right? So we start with 0 everywhere, and then we have minus 1s everywhere, except the terminal states, which don't change. And then we get to here and we have 2's, for example, in the middle. Why do I have minus 2's in the middle? Because again, the equation is the immediate reward, which is minus 1, plus the discounted future reward. Well, discount gamma is 1. If I said gamma is 1, so there is no discount. So and your future reward is basically the state that you end up in. Is summarized in the next. So if I'm in this state, no matter which action I take, I basically get minus 1 immediately, and then minus 1 is my current estimate for the long-term reward from the resulting state. So that's minus 2. And why do we have minus 1.7 here? And is it minus 1.7 or what's the exact number there?
75. Minus 175.
Right, so if I'm here, I have 4 actions. 3 of them give me, end up in states which are marked as minus 1. And 1 of them ends up in a state marked 0. Right, so I have the average of 3 minus 2's and 1 minus 1, which gives me 175. Yeah.
So in calculating throughout the iteration,
Mhm.
you use the previous iteration's values, right?
Correct. So that's called synchronous backup. So basically you take the old table, you keep it as it is, and then you start filling the new table based on the values from the old table. That's not the only way to implement these things. You can have asynchronous backups where everybody uses everybody else and things keep changing. You change one value at a time, etc., etc. But basically it makes no difference. They all converge. They all give you eventually the right solution. All right. 30 seconds for questions, because all of the other algorithms are going to be like this. We're going to iterate one of the Bellman equations, starting with some arbitrary 0 assignment. Okay? Now, let's talk about the control problem. Namely, how do we actually find the perfect policy? So, the first algorithm we're going to see for that is called policy iteration. It's very simple. It basically says find the value function of your current policy and then improve your policy by acting greedily with respect to that value function. Okay? That's it. And keep doing this, you know, until things don't change anymore. So we evaluate the policy to find v pi, and you can use the previous algorithm for that. And then after that, we improve the policy by acting greedily with respect to v pi. Now, can somebody explain why this actually changes pi? I mean, I got v from pi, and then now I'm acting according to that v. So why do I get a different policy?
So you are using uniform policy at first.
Uh-huh.
Then I choose the action that yields the higher value.
That's right. So
Policy changes.
actually, this is a good example, I guess, right? So these values came from a uniform policy, right? But obviously, the uniform policy was not optimal with respect to these values. Because, you know, if I'm here, for example, I don't want to go left or top up. That's minus 20. I want to go right or below. I want to actually get a smaller minus number, right? So that means a policy can give you a value function, but it may not be the ideal policy for that value function. You can actually have a better policy for that value function. And on the right-hand side here, we see the optimal policies for the different value functions on the left. So the greedy policy with respect to the vk on the left is given on the right with the little arrows. And it shows you that, for example, here, most of the places, the greedy policy is still indifferent because no matter which way you go, you get a minus 1. But over here, it starts being selected, right? So, for example, if I'm here, I prefer right. Why? Because if I go up left or down, I get a -2. If I go right, I get a -1.75. So over here, I prefer a right as well. So it becomes more selective. And after 3 iterations, actually, it settles, strangely. So at k equals 3, my evaluation hasn't converged yet. I don't have the real values yet. However, the policy is already the optimal policy. Notice that it doesn't change when I actually keep iterating the evaluation loop an infinite number of times. The optimal policy doesn't change. Okay? So this gives us the idea maybe I don't need to complete evaluating my original policy completely, right? I can just do this a couple iterations and then find an improved policy based on that value function, and that might actually result in a more efficient algorithm. Okay. And we can also prove that this policy iteration always converges to the right policy. And here's sort of the general picture that illustrates what's going on. So we start with a particular pi and a particular v. The pi that we started with in the last question was the uniform random policy, and the v we started with was 0, right? And then we basically go up, evaluating the policy and getting v pi, and then we go down, improving the policy by acting greedily according to that v. And now that the policy changed, we can repeat this over and over again, and eventually we converge to v star and pi star. And in fact, I'm not going to show you the details of the proof, but the proof that these things converge actually look like that picture. They basically prove that one iteration of the of this backup actually brings value functions closer together. What do I mean by that? So let's say I have 2 different value functions, v and u. They assign different values to the states, okay? And then I do one iteration of the this evaluation loop, and I can show that they actually come closer together. And that's basically called the contraction mapping theorem, and that's how people prove that these things always converge. Okay. So I'm skipping over some details. Now, one thing I guess that's worth noting is, how do I know when the improvements stop, I have actually found the right solution? Well, here's the thing. If the improvements stop, that means, so let's say I have pi, my current policy, and I do one iteration of this thing and I get pi prime, and pi prime are the same. Okay? So that means q pi is equal to the maximum value, because if it wasn't the maximum value, my greedy step would basically give me a different value, right? So maximum, the q pi basically gives me the value of the maximum actions q pi SA, which is basically equal to the v value. But then if the v value is equal to the maximum action q value, then that's by definition the Bellman optimality equation. If this is true for every state, then that means I've already satisfied with these v's and q's the Bellman optimality equation, which means I already have the optimum value function, and therefore the optimal policy. So we'll use other algorithms for the evaluation side and the improvement side, but the idea is always the same. Okay. So here's our second algorithm. So the first algorithm basically did value evaluation for a policy and then the improvement. It basically alternated these two steps. Now, imagine just updating the value function using the Bellman equations and not even bothering to look at the policy. Okay? But this time I'm going to use the Bellman optimality equation. So going back to our list of equations, my second algorithm, my first algorithm used the Bellman expectation equations on the left in order to evaluate the policy, and then used greedy action selection to improve the policy. Kept going back and forth. The next idea is, why don't we just try this and, for example, use equation 7 here as my backup operator. So again, start with a random v or v full of zeros, and then use equation 7, choosing the max instead of the sum of the next reward plus the discounted version of my future rewards based on the already existing tables I have. So that's called value iteration. Okay? So the previous idea was policy iteration. This idea is value iteration. Policy iteration uses Bellman expectation equations to evaluate a policy and improve it using greedy selection. Value iteration directly uses this. Okay? So, any questions about this second idea? Value iteration. Here is the same equation. So let's say S, well, when you reach the optimal policy and value function, this is the equation that needs to be satisfied. Every V has to be equal to the maximum over all possible actions of reward plus future returns. So why don't we just start with a random V and keep iterating. Well, I was going to ask you this, but now that I showed you, it doesn't work. So, so at least let's try to understand how this works together. So, again, so let's say similar to our previous problem, but we only have the goal state on the upper left, and we have -1 per action, and we don't know the value function, so we basically start with zeros. And now I'm not going to even bother with a policy. I'm just going to use the value iteration idea. So again, in the first iteration, all zeros turn into -1s because -1s are the direct rewards I'm getting, right? And after that, V2 to V3 turns some of these -1s into -2s. Why? Because you get -1 from the immediate action, and then -1 from the state that you end up in, right? Except for a couple close to the goal, those guys stay at -1. Why? They were -1.75 last time, remember, when we were doing evaluation. Why are they -1 now? So those two numbers on V3.
We directly use the value of the goal state.
That's right. So here, before I was evaluating a random policy. Here I'm basically taking a max. When I take a max, that means I don't actually have to look at all my neighbors. I just have to look at my best neighbor. And if I'm in one of those -1 squares, my best neighbor is the 0 neighbor, right? So then I'm saying, okay, if I'm here, I'm going to take an action toward that goal state. That costs me -1. And then once I'm in that goal state, I'm 0 forever. So that's -1. I don't need to worry about all the other states. Okay? So if you keep repeating this, you end up with this, where things actually converge, and each of these numbers actually represent the shortest path, the length of the shortest path from that square to the goal. And as you can see, so let's see, all of the numbers here satisfy the Bellman optimality equation. So if I'm at minus 6, okay, I can go down or right, which will have me stay at minus 6, or I can go up or left, which will have me stay at minus 5. So of course, since I'm basically choosing optimally, I'm going to choose left or up as my next action. So that means that action is going to cost minus 1, plus the long-term reward from the resulting state is minus 5. So that's basically still minus 6. So if I'm at minus 6, I'm going to stay at minus 6 forever. Okay? All of these numbers have that property, that they're consistent with their neighbors according to the Bellman optimality equation. Any questions about value iteration? So far we have 2 algorithms to find the best policy on a given toy problem. Policy iteration, value iteration. And here's sort of a summary of the 3 things that we've done so far. So when your problem is prediction, namely you're trying to, given a policy, find the value function for that policy, we just use the Bellman expectation equation and we keep backing up using that, and that's called iterative policy evaluation. When we use that plus greedy action selection, we basically have what's called the policy iteration algorithm. And if we use Bellman optimality equation instead, we get value iteration. So policy iteration and value iteration are the 2 of the control algorithms, and iterative policy evaluation is the prediction algorithm that we have seen so far. Questions? I'm skipping these parts really fast because I want to get to neural networks, which is a couple of lectures ahead. There are some extensions that I'm not going to go over, but basically you guys already came up with these ideas: asynchronous updates. We can do in-place updates. We can sort the updates according to some criteria, or but a couple of important ideas, important extensions of this that are going to form the basis of our real-life algorithms that actually work for problems other than toy problems. There are 2 such ideas. One is replacing these full-width backups with sample backups. Okay, what do I mean by that? So when I'm updating dk plus 1 for s here, what do? I look at all the possible next states I might end up in, right? So that's called a full width backup. I'm looking at the full tree. I'm only looking 1 step ahead, but I'm looking at the full width of the tree in order to calculate my next value. Now, first of all, there's 2 things that are wrong about this. The first thing is, what if you have a problem that has infinitely many states or very large number of states? Okay? So if you're trying to fly a helicopter or something, then all your states are continuous. So this tree does not look like a tree. You know, your next state can be a continuous number, right? Or in problems like playing Go, your next state might have 300 different moves, okay? So that might make looking at this full tree, even for 1 step, pretty expensive. But more importantly, in order to do this full width backup, I need the R and P matrices. Remember, in the equation, when I'm doing the backup, for example over here, or let me say over here, I basically have this R for every state action pair, which was given to me by my model, and I have this P matrix, which basically says if I'm in state S and I take action A, what is the probability of getting into state S prime for every state action pair state action, next state triple. Okay, so these are given to me as a model in an MDP. So remember that MDP consists of set of states, set of actions, the P matrix, the R matrix, and the gamma discount factor. If I know all of this stuff, I can do these calculations. But typically we don't. Typically I don't know what R I'm going to get, and typically I don't know what S prime I'm going to get pushed into. I basically learn these things by experiencing them in normal reinforcement learning problems. If I'm trying to teach a robot to walk, it does something with one of its motors, it doesn't know where the environment is going to push it in the next state. It actually tries it and sees where it ends up in. So I don't have that full picture. I don't have that full tree. Okay? So one big idea is going to be, instead of using this full width, can I just use one sample out of this tree? So let's say if I'm actually experiencing this in real time, I'm going to take one of these branches, and then the environment is going to push me into one of these S primes. And is that enough? Maybe that's enough. Maybe I'll just use that particular S prime I ended up in and do a backup from that instead of doing this whole tree thing. Okay? So that's sort of the full width versus sample logic. So so to summarize everything I said, instead of the reward function R and the transition dynamics P, which I don't know normally, I'm going to basically look at starting state S, the action I'm going to take A, the reward and state I transitioned into R and S prime as a sample, and I'm going to design my updates around those samples. The second big idea, which basically takes us to deep Q learning or deep reinforcement learning, is function approximation. Especially in problems where there is a lot of states or infinite number of states, it doesn't make sense to have value functions stored as tables. Okay, in all of these toy examples, we basically had a 4x4 table where all our values are stored in. But if you're solving a finite problem like Go or poker, those tables are huge, and you can't store them. There's just too many states to store values in. So we use function approximation. So instead of basically saying V of S, we basically say V of S is a neural network. I'm going to feed S into this neural network, and the neural network is going to estimate the value for me. Okay, I'm going to initialize this neural network randomly, and then when I'm training it, I'm going to show it as targets, the Bellman targets, right? Because each V of S is related to its neighbors, so I'm going to do that and train my network. So for example, here's an example. With the Bellman optimality equation, I'm going to take this as my target, this from my current neural network, and then use that as a supervised learning target for my current neural network. Okay, so those are the two ideas that we will take to extend. So, as I mentioned before, the way we prove these things actually converge is using this contraction theorem. So I just want to briefly show you, it's not very difficult. We basically imagine V, the whole value vector, as living in some vector space. And then this Bellman step that we update V as a transformation in that vector space. That transformation map takes any vector in that space and maps it to another vector, right? And the idea is, so I call that T pi. The transformation is T pi. Okay, so T pi of V, the transformation of V by this Bellman equation, is equal to R pi plus gamma T pi V. So this comes from the Bellman expectation equation. This is the vector form of the Bellman expectation equation. This is how I would write Vk plus 1 in terms of Vk in my iterations, right? And then you can show that if you start with two different value vectors, u and v, okay, the distance in infinite norm, which means the maximum value that they're different in, the distance between them according to some norm is actually going to decrease. So u minus v, or gamma times u minus v, is the original distance. After I transform them, they actually come closer together. Okay, so that's the idea of these proofs. Any questions? You're not responsible for the contraction theorems. This is just for your general information. Okay. So far we basically saw an algorithm to evaluate a policy and two algorithms to optimize a policy. All of these algorithms use the Bellman equations, but they also use the model. So they actually needed the P's and the R's in order to do their calculations. So now we're going to talk about model-free methods. Model-free methods, as I said, don't have access to P and R, so they have to sample and do something. Yeah?
You said there are a couple of versions in post-iteration, like synchronous or asynchronous.
Right.
What is the difference? They converge to the same thing?
They converge to the same thing,
So
yes.
the speed, just what is the difference?
Some of them converge actually faster. If you do the updates in a particular order, you might actually converge faster. So what do we do if we don't have a model? What do we do if all we have is experience? Right? So we don't know how the world works. We just try different things and receive different rewards and actions. We're going to do, I don't know. I want to use this thing. Oh, that worked. So we're going to have two ideas. In value iteration, where do my targets come from? How do I update my beats? What do I look at when I'm updating my beats? I look at all my neighboring states and their older V values, and I take the best one, combine it with the immediate action and the discount factor, and that basically becomes my target value. It's not the correct value maybe yet, but it's a target that I basically try to approach to. So what else can I use as a target if I don't know these things, if I don't know the transition probabilities and rewards? Well, I can do the, I can play the game to the end for one episode. I can see all the future rewards. Once you see all the, state, action, reward triples from now to the end of the episode, then you can use those as one sample from the real world of what this state is worth. Okay? So I'm in state 1. I take 100 actions, which result in 100 different states and rewards, etc., and then the game ends. And at that point, I know exactly for that particular game how much my current state was worth in the beginning. Okay? So I basically do this discounted calculation for that whole episode, and I use that as my target. That's the Monte Carlo method. Yeah?
How could you say the game will end, for example, in maze if you go randomly? equation.
Right. So the Monte Carlo methods that I'm going to mention only work for finite MDPs. Okay, so for infinite games, we're going to use TD. So these things actually require the episodes to end at some point. Okay, so here's our little history. I basically have a current policy. I play the whole game from S1 to SK. And then we know what the return is. The return is always defined as this thing, right? And remember that value function. I mean, before we defined all these Bellman equations and stuff, the real definition of the value function is the expected return. And the return is basically all of those rewards added together with discounts. So basically, why don't we just use these equations directly? And instead of this expectation, I'm just going to use the actual return I got from this game. Now, what's wrong with this? Why would this give me the right solution or not give me the right solution? So, for example, if I did this for one game, and then I basically updated all the values for the states I've seen during that game, based on all their future rewards and stuff, would I actually have the right values? Am I done?
You don't know if the policy is optimal.
Let's talk about evaluation. Policy is fixed. Maybe I'm doing the random policy. So I play one game with the random policy, and then depending on what the rewards and states I get, I update all the states that I've seen during this game. Are these values correct values?
There may be some unvisited states.
That's right. So I don't know anything about unvisited states. That's problem number one. But even for the states that I've visited, is the value I calculate for this state correct?
It's just one sample.
One sample. So does that mean if I actually play it again, am I going to get a different value here? Why? What will change in the second game? I'm still applying the same policy.
It might be a random policy.
But
Yeah, well, my policy might be random, that's right.
the environment is random.
The environment is random in two ways. The rewards it gives me are random. The states it throws me at are random. So if I play the same game twice from the same exact state, I'm not going to get the same return again, right? That's why there is this expectation here. Because I don't, there's a lot of things that are undeterministic. So then what I'm getting is exactly like you said, one sample out of this uncertain thing. But we know that if we get enough samples and if we average them, eventually we'll get the right value here, right? So that's the thing. So I'm trying to get the real expectation of return. Instead, I play 100 games, and for all the states I've seen, I basically update their values to reflect the average return from these 100 games that I have. Okay, so that's Monte Carlo. So there is again, just like synchronous versus asynchronous, there's slight variations in how you can implement Monte Carlo. One is first visit versus every visit. This might be a little bit of a detail, but let's just briefly mention it anyway. So states might repeat, especially in small games. I might revisit the same state over and over again during an episode. So every time I visit that state, I have a different return starting from that point in time forward, right? And then I visit the state again in 10 steps, the same state, but now I'm closer to the end, so my return will be lower, okay? Or if I have fewer terms, it might be higher. Maybe the returns are negative, I don't know. So that means for the same state from the same game, I'm getting several different values. What do? Well, I can do two things. I can use all of them, which is named every visit Monte Carlo, or I can just use the first one and ignore the other ones, which is named the first visit Monte Carlo. Okay? In the first visit Monte Carlo, the first time step t that I visit S, I basically increment the counter of how many times I've seen this state and increment the total return, and at the end basically I set vs to the mean, namely the total divided by the number of times I visited that state throughout all my games or episodes. Any questions? And every visit does it for every visit. We can skip the example. The other variation is basically the mean calculation. It's one thing to wait until the end of 100 games and then calculate all the means, but it's another thing to just keep calculating the means incrementally, right? So if I'm throwing you a bunch of numbers, you're sitting at a particular state, I keep playing games, and I give you 100, I give you 70 for that state return, I give you 80. You can keep a running mean, right? So you can basically keep updating your mean as more and more numbers come in. How would that work? Well, you can take your old mean, and then you can take your new value, and the difference between new value and the old mean, divide by k, add to the old mean. You can basically incrementally update, keep updating your mean. So this would look like this. Each time there's an update, you increment the counter n, and then you increment the mean. You increment the value with this from the incremental mean calculation. Now, why am I showing you this? This is just a mathematical trick. But this equation actually is interesting because this looks like a weight update from our neural networks. Right? This looks like the learning rate. And basically, this whole update basically tries to get Vs closer to GT. Right? It just pushes it in the direction of GT. So this GT minus Vs is almost like my gradient. Okay? So if you see that in that picture, then we can actually do some more generalization and actually stop wasting time with means and stuff and say, I'm going to do this. I'm going to have a learning rate alpha. Okay? And every time I observe a GT, every time after a game there's a new return, I'm going to take that as my target. So this target minus my current value becomes like the error or the gradient, and I'm going to take a step to reduce this error. So it's basically turning this into almost a neural network type training step. Okay? So that's Monte Carlo. I'm going to, and we only talked about evaluation so far. We didn't do control. We're not optimizing, we're just evaluating. Okay? And all Monte Carlo does is basically says play 100 games and then look at the average returns you get for each state. Any questions? It's model free. It's not using R or P. It's only using the experiences that you have. So the other model free idea is temporal difference learning. This is also model free, and it has the advantage of being able to update its values from incomplete episodes. So that means I don't have to wait until the end of the game. I can basically keep updating my values after every move, and that way, this is why TD learning can be used for infinite games, for example. Okay. All right, so I guess the approaching a particular target idea is the right sort of framework to understand TD versus MC. So if you look at this equation here for MC, Monte Carlo, I said, oh, we're doing this update because we're trying to approach this red GT target, which is the return of the last game that we played for this state, right? Now I'm going to change this target, and instead of being GT, I'm going to turn it into reward, the immediate reward plus discounted version of discounted value of my next state. Okay? So this should be familiar from the Bellman equations. The Bellman equations say if you want to evaluate a particular value, if you have the right value function, then it should obey the equation that Vs should be equal to the immediate reward plus some discounted version of future rewards. So here, I'm basically taking that for this one particular sample. So I go one move, okay, I'm in state S, I take one action, I get a reward, I get a next state, I look at the value that I have assigned to this next state, and if everything is correct, then my current estimate should be close to RT plus 1 plus discounted version of the value that I assign next state. I try to enforce this consistency. So V of ST should be consistent with V of ST plus 1. So this becomes my target. So if you notice the red parts, in MC, the return is the target. In TD, immediate reward plus the next state is the target. But other than that, it's the same type of update. So now I can update after every move. I don't have to wait until the end of the game. I don't have to run several episodes. Every time I take a step, it gives me a new target. Okay? Any questions about TD?
How do you estimate the V value?
It starts 0. All the V's start at 0. Right? And then they basically... So imagine all the values are initialized to 0, and then every time you take a move, you basically say, oh, here's the immediate reward I got, and my next state was this, and my value function currently assigns 0 to this. So let me update my current state's value to that, multiplied with some learning rate. So this is the TD idea. Temporal difference learning. Okay. So what is the difference between TD and the first thing we saw, iterative policy evaluation? Iterative policy evaluation also used the bounded expectation equation, and it also updated all the V's to be consistent with their neighbors, I guess, right? So the thing that you did on paper, it looks fairly similar to this. What's the difference?
There was an expectation or maximization.
There was a sum,
Some, yes.
right? So what you did was basically taking a sum over all the possible next states,
It's just
and
one.
this one is only taking one next state. Okay, that's the big difference. So the other one was calculating the real expectation because it had probabilities and stuff. This one is basically replacing that with a single sample. I'll do this example in a little bit. That's examples I want to. Yeah, so I wanted to show you this. So when you're doing Monte Carlo, let's say this is the whole game tree or your environment interaction tree. Right? So you're in a particular state, you take a particular action, the black nodes are the environment, the black node basically gives you a reward and sends you to a different state, and then you're white again, and then you play, they play, etc., and then these T's are terminating states, and you look at you're trying to calculate the value you get from these interactions, right? So Monte Carlo says, forget about this tree, I'm just going to go down one branch all the way to termination, and I'm going to use the values I saw during that interaction. That's Monte Carlo. Okay? TD says, no, we don't need to go all the way to the end. Let's just go one step, and let's make sure V of S is consistent with V of S prime. Okay? So I'm going to basically construct a target for ST using RT plus 1 and ST plus 1. Okay? I'm going to enforce myself to be self-consistent. And here's the dynamic programming, or the first thing you did, which is using the model. It basically looked ahead one step again, it updated V of S in terms of an expectation about V of S t plus 1. But it basically looked across the whole width of the tree. Remember I mentioned, sample from the tree versus look at the whole width of the tree. So in iterative policy evaluation, we basically go one step ahead, but we look at the whole width of the tree, which means we're basically taking a sum over all actions and all states in the next step. And this is sort of the summary of this lecture in general. So on the x-axis, we're basically looking at shallow backups versus deep backups. What I mean by that is shallow backups only look at 1 or 2 steps and use that as the target, whereas deep backups go all the way to the end of the game and try to generate some value from there. In the y-axis, we basically have sample versus full. This refers to the width of our analysis. X-axis refers to the depth. The y-axis is referring to the width. In full backup, like in dynamic programming, I'm looking at the whole width of the tree. I'm considering all my actions and all the possible states that the environment can send me to. Whereas in sample backups, I only know the one game I played, so that one very thin thread becomes my input, where I construct my target from. So that basically gives me 4 possible algorithms. On the upper right, I basically have the whole tree. If I had the whole tree, and if I had the whole model, I could basically look at this tree and solve this problem exactly. It would be expensive maybe, but I have the exact values for everything. On the upper left, we have dynamic programming, which is the iterative policy evaluation that you did in the beginning of the class, which basically means look ahead one step, but use your model to consider all actions and all states for that one step when you're updating your thing. And the bottom part consists of the 2 algorithms that I mentioned toward the end. Monte Carlo looks all the way to the end to generate the target, whereas TD only goes one step to generate the target. Yeah.
How does the sample size affect?
So Monte Carlo is, first of all, unbiased, because you're basically calculating the exact thing you're trying to take the expectation of, but it has very high variance. Well, how do I know it has high variance? As I mentioned earlier, if you're in the same game, in the same state, if you play 2 different games, you'll get very different Gs. So that's high variance, low bias type of setting, unbiased type of setting. TD learning only is taking one step. So it's going to be relatively lower variance, right? So think of the variance of your return when you play the whole game versus variance of the estimated return for TD when you just take one move. Okay, so TD is going to be much lower variance. On the other hand, the target that you get from TD is fake. You didn't even finish the game yet, right? You're basically using the entry in your own table as your target, training target. So it's totally biased, okay? And under some conditions it converges, under others it doesn't. And we'll see, what those conditions are. Any other questions? All right, I'll see you on Thursday.